We're going to look at the LeetCode problem 215. Kth largest element in an array. Given an integer array nums and an integer k, return the kth largest element in the array. Note that it is the kth largest element in the sorted order, not the kth distinct element. Can you solve it without sorting? So here we have the inputs k is equal to 2 and the output should be 5. So basically the kth largest element is based on the sorted order and the duplicates are considered and the constraints suggest a large input size, that is n could be up to 10 to the power 5 and integer values in the range minus 10 to the power of 4 to 10 to the power of 4. So the possible approaches here could be we can sort the array in the descending order and return the element at index k is equal to 1. Sorry, at index k minus 1. And here the advantage is that it's very simple to implement, and but the disadvantage here is it requires O of n log n time for sorting, which is inefficient for large arrays. And the problem explicitly asks for the solution without sorting. So the time complexity would be O of n log n for sorting and O of 1 for assessing the kth element, which is O of n log n, and the space complexity would be O of 1 if sorting in place, that is array with arrays dot sort in Java, or O of n if additional space is used. And we could use min heap priority queue of size k. We could use a min heap to maintain the k largest elements seen so far. For each element in the array, if the heap size is less than k, then we add the element. If the heap size is k and the current element is larger than the heap's smallest element, we remove the root and add the current element. After processing all elements, the heap's root is the kth largest element. So the advantage here is it's efficient with O of n log k time complexity. It's suitable for large arrays and it avoids sorting, and it uses limited space, which is the heap size k. And the disadvantage here is it requires heap operations which are slightly more complex than sorting. So the time complexity would be O of n log k and space complexity would be O of k for the heap. And the next third approach would be max heap priority queue for all elements. Add all elements to a max heap, then remove the top element k minus 1 to get the kth largest. So the advantage is straightforward heap usage. The disadvantage here is it requires O of n space for the heap and O of n plus k log n time, which is less efficient than the min heap approach for large n and small k. And the time complexity here is O of n to build a heap and O of k log n for k removals. And the space complexity would be O of n for the heap. Then the fourth approach is the quick select, which is partition based algorithm We can use the quick select algorithm, which adapts quick sorts partitioning to find the k the largest element by selecting a pivot and recursively searching only one partition. The advantage here is that average case time complexity is of n, which is theoretically optimal. And the disadvantage here is its worst case time complexity is of n square if pivots are poorly chosen, and implementation is more complex, and random pivot selection is needed to avoid worst case scenarios. So the time complexity is of n average and of n square worst case. The space complexity is of n 1 if implemented iteratively and O of log n if recursive. So I'm choosing the min heap of size k approach. I'll use the min heap approach for the following reasons: efficiency as a predictable of n log k time complexity, which is efficient for large arrays, especially when k is much smaller than n. Example, k is 2 and n is equal to 10 to the power 5. This is better than sortings of n log n and often faster than max heaps of n plus k log n when k is small. And space efficiency uses O of k space, which is minimal when k is small compared to O of n for a max heap. Simplicity, easier to implement and understand than quick select, with no risk of n square worst case performance. And I want to use priority queue heap priority queue here because this is a problem is selected from this list, and I wanted to uh, use heap here. And so let's talk about time and space complexity. The time complexity is like heap operations, inserting an element into a min heap size of k takes O of log k. Removing the root smallest element from a heap of size k takes O of log k. So processing the array for each of the n elements in nums, if the heap size is less than k, insert the element of log k. If the heap size is k, the element is larger than the heap's root. Remove the root and insert the element of log k, and of log k gives of log k. So in the worst case, we perform O of log k operations for each of the n elements. So total O of n log k as we process n elements, each recurring up to O of log k heap operations. For initialization, creating an empty priority queue is O of 1 and no additional pre-processing is needed. And if you want to talk about space complexity, the min heap stores at most k elements at any time, that is O of k. So no additional significant space is used. Example, no recursion or auxiliary arrays. And so let me go ahead with coding. So I'm going to initialize the priority queue now. Oh, okay, yeah, that's a typo there. Actually, we don't even have to do the input, it's already there. Okay, that's better. That's good, I guess. And let me try to explain this code. What I'm trying to do here is so here the method, it takes the integer array nums and an integer k as an input, and the goal is to return the kth largest element as an int, and here we are creating an empty min heap using Java's priority queue. So by default, priority queue orders elements in ascending order, smallest at the root, which suits our need for a min heap. And the heap will store integers and maintain at most k elements. And here we are going to iterate through each element num in the input array nums, and for using a for each loop, and then here we are checking if the heap has fewer than k elements. If true, we can add more elements to reach size k, and here min heap dot offer of num, it adds the current element num to the min heap. Offer inserts the element and maintains the heap property in O of log k time, where k is the current heap size, and if num is greater than min heap of peak, if num is greater than min heap dot peak, here if we are checking if the the heap already has k elements, and if the current element num is larger than the smallest element in the heap, which is accessed through peak, then peak returns the root of the min heap, that's the smallest element in O of one time. So if the num is larger, it could be one of the k largest elements. So we proceed to update the heap, and then here min heap dot pull basically removes and returns the smallest element from the heap. Pull takes O of log k time to remove the root and reheapify. So this step ensures the heap size remains k by removing the smallest element before adding a larger one. And then we have min heap dot offer of num. So this basically adds the current element num to the heap, maintaining the heap properly, and it takes off log a time, and after processing all the elements, the heap contains the k largest elements, and the root is the kth largest element. It returns the root using peak in O of one time. So I'm gonna have an example walkthrough now. So let's say the input nums is 3, 2, 1, 5, 6, and 4, and k is going to be 2. So we want the second largest element, and the expected output is going to be 5. So initially, so the initial state, we have an empty priority queue, and here the goal is to maintain a main heap of size 2 containing the two largest elements seen so far. So we are going with the iterations now. The first element is num is equal to 3. We are the loop now, so we are looping through num. So the first element is 3, and then main heap dot size is equal to 0, so which is less than 2. So we are adding the 3. So now min heap has this element 3. So the next element is going to be 2. Num is equal to 2. And here min heap dot size it's going to be 1 now, and which is again less than 2. So we add what's the next element? 2. Sorry, the current element is 2. And so then now the min heap is going to have the elements 2 and 3. So basically 2 is the root and 3 is the child, and then the next element is going to be 1. So min heap size is 2. So here what are we going to do? We are going to check if 1 is greater than min heap dot peak. So which is basically 2. So min heap dot peak gives us 2. So like we are checking if 1 is greater, if num is greater than min heap dot peak, and so now yeah, because like 1 is less than 2, so we skip this part. So what does it mean? It means 1 is not among the top 2. And now the min heap is going to have the same elements 2 and 3. So next element is going to be 5. Num is equal to 5, and min heap dot size is equal to 2. So we are going to check. So this condition doesn't satisfy, so we are in else if now. So we are checking if 5 is greater than min heap dot peak. So min heap dot peak is going to return 2 again. So we are checking if 5 is greater than 2. Yes, it is. So what happens? So we are removing here. So remove the root, which is 2, and add 5. So here we are removing the 2 and we are adding 5 here. So after pull, min heap becomes 3. It has only 3. And after 4 of 5, min heap becomes 3 and 5. Now what's the next element? The next element is going to be 6. So num is equal to 6, and min heap dot size is equal to 2. So we are in else if now, so we are checking six is greater than min heap dot peak. Which is going to be 3. Yes, 6 is greater than 3, so remove root, which is 3, and add 6. So after pull, we have min heap is equal to, so we remove the root 3, so it's gonna contain only 5, and after offer of 6, min heap is going to have 5 and 6. So yeah, we do have another element. It's 4. The next element is 4. Num is equal to 4, and min heap that size is going to be 2 again, and so we are checking if 4 is greater than min heap dot peak. So that's gonna give us 5, which is 5 again. So here 4 is less than 5. So we have to skip the else loop to else if block 2. So skip. So what does it mean? It means 4 is not among the top 2. And now the min heap is going to have 5 and 6 as previously. So yes, the for loop completed. So the final state min heap is having 5 and 6, and the peak of this one, let me write that one to the final state. The final state min heap is going to have 5 and 6, and now the min heap dot peak is going to return 5. So this is the smallest of the 2 largest elements, 6 and 5, which is the second largest. So the output is going to be 5, and so I have handled the edge cases here. If k is equal to 1, it returns the largest element, because the heap size is 1 and we keep the maximum element seen. And if k is equal to nums dot length, it returns the smallest element. The heap contains all elements and the root is the smallest, and for duplicates it's handled naturally, as a heap compares elements and keeps the k largest including duplicates. And for negative numbers, it's handled as a heap compares integers regardless of sign. And for single element, if the nums dot element is equal to 1 and k is equal to 1, it returns the only element. And so this basically works because the min heap maintains exactly k elements, ensuring that after processing all n elements, it contains the k largest elements in the array. And the root of the min heap is the smallest of these k elements, which is precisely the kth largest element in the sorted order, which is a descending order. And here, and by only adding elements larger than the heap's root, we efficiently filter out smaller elements, keeping the heap size at k and achieving O of n log k time.